Okay, so let us start the second part. So I didn't clean this because I didn't want to confuse you. I prefer to write a formula like this by changing y to x everywhere. So I hope that you are not confused. I am just jumping from x to y, y to x. But as far as they are actually from the correct domain, x means the input. So it doesn't matter. So it means that if I choose my input from the domain of f inverse, and I know that this is the case, f is differentiable at f inverse of x, and it is not equal to 0, I have this relation. So I rewrite this relation instead of, I wrote it with x, because if I have a function, we usually are used to put x in front of our functions, not y. That's up to you, okay? So now let us do the next example. So this is the only example that I want to solve of this one. So if I show you, show that the function f of x, which is defined in this way, is invertible, and determine f minus f inverse prime at 2. Well, it's a very standard question, and it is usually not that hard. Okay, so a function is given to me, and f of x is equal to 4x cubed divided by x squared plus 1. This question has two parts. First, you are supposed to confirm it is invertible. So the first thing comes to mind is to use the derivative to show that this is strictly increasing or decreasing. Okay? So let us take our chance to calculate f prime. So f prime, if you don't mind, let me take this 4 out. Okay, it doesn't matter. Okay, so let us work with 4. This is the quotient rule. So the derivative of a quotient becomes the derivative of the numerator, which I can write 12x squared, and multiply it by the denominator itself, minus the other way around. Minus the derivative of the denominator, which is 2x, multiplied by the numerator itself, and then divide everything to the power, the denominator squared. Let us simplify this a little bit. So if I multiply this here, it becomes 12x to the 4th. This becomes 8x to the 4th. Positive, negative, so it becomes 4x to the 4th. Yes? And then I have 12x squared. So if you want, I can factor 4. You don't have to, but let us factor 4x squared out. So this becomes x squared plus 3, and then divided by x squared plus 1 to the power of 2. Okay. But is it greater than 0 strictly, or greater than or equal to 0? Which one is that? This one is strictly positive, because this is non-negative plus. This is always positive, and this is positive. But this one might be 0, okay? So in principle, this is not strictly greater than 0, it is greater than or equal to 0. So I am a little bit in trouble now, because I need a strictly increasing. Yes, I need that adverb strictly, yes? But is it strictly increasing about what we discussed before? Because if I put equality, in how many places it occurs? But, so, I would say that, but, since f prime of x equals to 0 occurs only at which point? If I want to make this fraction equal to 0, there is only one choice, x equals to 0. And that's an isolated point. Yes, occurs only at x equal to 0, f is, you need to explain a little bit, because that's an isolated 0, f is strictly increasing. So this means that f is 1 to 1, this means that f is invertible. Okay? You have to explain them when it comes to exam. Okay, but now the question is asking you for this one, this function, which is now confirmed to be invertible, can you calculate the derivative of f inverse, but calculated at 2? This is what we want to calculate. So I will use this. I mean, let me use the formula first. So it means that in this formula, I will replace x with 2. Okay? So what happens? F inverse prime of 2 becomes equal to 1 over f prime calculated at f inverse of 2. Okay, so in order to answer the question mark, what do I need? Instead, because this is my question mark, I have to calculate this expression. For calculating this expression, I need two things. I need my derivative, which I have it. I have it at every point. I also need one more thing. I need f inverse of 2. So still, this is another question mark. Okay, I don't know this. But I have to calculate that, okay? I want to know f inverse of 2. I don't know what is f inverse of 2. It doesn't matter what you want to call it. For example, let me call it, I don't know, y. Whatever you want, alpha, beta, or whatever. And you want to find this y. So what do you calculate? What does it mean? It means f of y is equal to 2. Is that right? I am looking for y. But what is f of y? It is simple. It was better to choose x. It doesn't matter. F of y becomes 4y cubed divided by y squared plus 1 equals to 2. Are you following? Okay. But now the point is that in principle it should be doable because I am looking for y and I have one equation for y. But there is one more problem here. This equation for y is not a usual equation because usually the first degree equations can be solved easily, the second degree using PQ or ABC formula, but if the degree goes higher, in principle I'm in trouble. Okay? But here, can you tell me what the answer is? Can I guess here and make sure that I am done?
Y.
Guessing is easy. What is y by guessing?
1.
Yes, y is 1. But this is, you shouldn't, you need to ask me, okay, Baba, how do you know that's the only one? That is important. You have to answer this question as well.
It is strictly increasing.
What? It is strictly increasing. It is 1 to 1. What does it mean? It means that no other number will be mapped to 2 by this function. Because this function is 1 to 1. If you could guess that 1 is mapped onto 2, because it is 1 to 1, there is no other solutions. So guessing here is okay, but you have to explain this in the exam. Okay? So this means that y equals to 1 works. How do I know this is the only one? Because the function is invertible, it's 1 to 1. Yes? So this is something you have to explain here. So this means that the y that I was looking is 1. This means that instead of this question mark, I put 1 here. Okay, so this means that the original question mark, which is f inverse prime calculated as 2, is 1 over f prime. F prime at which number? At which number? 1. 1. Do you agree? So that is the only thing that I want you to understand. You see, f inverse prime is 1 over f prime. But the number, if it is 2, it is not always the same number here. It is the f inverse of that number that you put there. Okay, that is easy. And then it is very simple now. Because I have calculated f prime at any x, I need f prime of 1 here. So I will go back here and then calculate f prime of 1. It means I replace x with 1 in my derivative with 1. Everywhere. So this becomes 4, this becomes 4, 16, and this becomes 2 to the power of 2, 4, so it is 4. And then I go back here, so what is the answer? It's 1. Yes? So it's a typical example. Any questions? Okay. I mean, the next part of the lesson might be a little bit easier. Hopefully you know these things from your high school studies. So let me just now we want to talk about exponential functions. Yes? So, do you remember from your previous studies what's an exponential function? If I have f of x equals to a to power x, a is constant, x is variable. This is called an exponential function. Do you remember if it was the other way around, x to power a, it's a power function. Okay? But there are some restrictions for this a as well. A is positive and a is not equal to 1. When I talk about an exponential function, I will always stick to this convention. A is not equal to 1 is very clear. Why?
1 power x is...
Because if a is 1, and 1 to power x is just 1, it's not exponential, it's just a constant function. But that is obvious that I have to rule that out. But if a is negative, then I will have some troubles. Because, for example, if let me take a to be minus 1. Then I will be really in trouble if I want to talk about these functions. This is not an exponential function. We can talk about this function, but we have to consider it case by case. Yeah. For example, if I choose x to be 1, the output is minus 1. If I choose 2, it becomes 1, no problems. But if I choose 1 over 2, then I am in trouble because minus 1 to power 1 over 2 means the square root of minus 1, which is not a real number. But then again, if I choose 1 over 3, that's okay, because this becomes the third root of minus 1. So it means that I will be in trouble about the domain. I cannot talk about something very specific if I want to investigate the function. So this is why we have these two conventions. Okay? Is that understandable? Okay, and then, but when I say a is greater than 0, so if this is 0 and this is 1, this one is excluded, and this one is 1, this is also excluded. A should be greater than 0, so I will take, this is the a value. If I give you the a axis, I can be here, or I can be here. It doesn't matter, both of them will be called exponential function. For example, if I write 2 to power x, this is an exponential function. If I write g of x equals to 0.5 to power x, that's also an exponential function. But there is a little bit difference between behavior of these exponential functions. Here, I am choosing a after 1. Here, I am choosing a between 0 and 1. So, both of them are called exponential functions, and the base, in one of them, the base is 2, in the other one is 0.5. Can you tell me, what is the very good, obvious difference between these two exponential functions?
The first one strictly increases.
Yes, it decreases. Yes. So if I want to, for example, draw the graph of this function, it will be like this. And this one, this is y equals to 2 to power x. When I make x bigger and bigger, the value of the function also becomes bigger and bigger. What is this number? Can you tell me?
1.
Yes, because if I put x equals to 0, then 2 to power 0 is 1. But what do you think will happen? Do you think it will reaches to the x-axis at some point? When I make x negative values and bigger and bigger negatives, what happens? For example, if I say 2 to power minus 2, the answer is 1 over 4. But if I tell you 2 to power 1 minus 1000, it becomes 1 over 2 to power 1000, which is a very, very small number, but it's still positive. Okay? So this means that as I go to the left, the distance between the graph and the x-axis becomes smaller and smaller.
The limit is 0.
The limit is 0. So this means that in this case, if a is greater than 1, the limit of a to the power of x goes to minus infinity is 0. The limit of a to the x when x goes to plus infinity is what? When I go to the right, it becomes infinite. Okay? If this is a greater than 1. Okay, what do you expect for the behavior of the limits if A is the other scenario, is between 0 and 1? If I want to draw, for example, the graph of this one, what do you guess will happen? If I make x a very, very positive large number, what do you expect?
It's 0.
It becomes 0 because, for example, yes, it becomes very small. So if I have this one to power 2, it becomes 0.25. But if I raise it to power 200, it becomes 1 over 2 to power 200. It becomes 1 over 2 to power 200, which is negligible. So this means that if A is between 0 and 1, I have written everything down there for you. So if A is between 0 and 1, what happens? The graph will be like this. Yes, so if I go to the right, it means that if x is extremely big, the function becomes negligible. But if I go extremely to the left, the function goes up to the infinity. Yes? So I mean, remembering these pictures will help you actually to have these in your head. And I hope that you agree with me in both cases. Can you say what is the domain? If I choose A positive and not equal to 1, then I do not have any restrictions for x. I can plug any value for x. So it means the domain is the whole real number. Yes? So the domain is always the whole real number. But what is the range in both cases?
Strictly greater than 0.
Strictly greater than 0. Why strictly greater than 0? Because it will never actually reach to 0. Yes? So if I ask you 2 to power x equals to 0, it will never happen. Yes, you can make it a smaller and a smaller, but it is not exactly equal to 0 anymore. So that's why it doesn't touch the x-axis. So is that understandable? But these are very simple ones. And I hope that you already remember all these formulas from high school. So yes, these are the rules. If I want to multiply two power exponents, with the same basis, I write the base and I add the exponents. And these simple things, if you don't mind, let me skip. Okay. So now logarithm. So how much do you know about logarithm? Do you remember it from your high school studies? Let me tell you somehow. If I give you, I want to define you a logarithm, what do I mean by that? So I would write logarithm of a number b to the base a. Okay? What do I mean by this symbol? First of all, when you see this symbol, b should be positive, a should be positive, and a should not be equal to 1. Otherwise, this doesn't make sense. We say that logarithm of b to the base a is x if and only if this happens. This number, which is the base, raised to this number is equal to b. So that is the formula. So it means that whenever you want to see an equality expressed in terms of a logarithm is true or false, you translate it into the exponential form and ask yourself, is this new one true or false? If this one is true, the other one is also true. If that one is false, the other one is also false. For example, or in other words, when you want to calculate logarithm of b to the base a, and if you want to know the number, this is the way that you have to think. This is asking about a number so that when this number is raised to that number, it becomes b. For example, when I say logarithm of 8 to the base 2, it is asking me, give me the number, so that this number raised to that becomes what? 8. Sometimes we can do it in our head, sometimes we cannot, so we have to use the calculator. Okay, so what's the answer to the question mark here?
3.
3. So this means that logarithm of 8 to the base 2 is 3. Yes? It means this one. Okay, so I will solve more harder problems for you, but this is the idea. And there is one convention. If the base is 10, we don't write it. For example, when I say logarithm of 100 without putting any number here, you have to assume that this number is 10. So in other words, this means logarithm of 100 to the base 10. And this is asking you, can you give me a number so that 10 raised to that number, it becomes 100? What's the answer?
2.
2. So that's 2. But if I, for example, if I ask you what is the logarithm of 99, that's the same thing. It is asking me about a number so that when I raise 10 to power that number, it becomes 99. Yes? But I cannot guess that number. But I know that that number exists. Why that number exists? I know something. I know this number is less than 2, because if it is 2, it becomes 100. And it is bigger than 1. Because 10 to power 1 is 10, 10 to power 2 is 100. So this number, whatever it is, it should be between 1 and 2. And of course, calculus will help you to see how much it is closer to 1 or closer to 2 later. But why that does exist? Because if I draw the graph of the function 10 to power x, it would be one of these type of functions. Yes? And this is 1. So if I go to the height 99, I can reverse engineer that, and this is your question mark. That question mark exists, but I cannot calculate it without calculator or other more advanced methods. Okay? But that is important that you know. Sometimes we can calculate it in our head, sometimes not. But according to the module, there will be some questions. So they have written that you have to be very good in calculating these logarithms. Okay, so they will not allow you to use calculators, so you have to be able to do it yourself. Okay, one question. If I want you to draw, for example, let us consider one case. A is positive, A is greater than 1, and then I have this function f of x equals to a to power x. And then I will also have another function g of x is equal to a logarithm of x, logarithm of x to the base a. These are two different functions, yes? How they are related? Is there any relation between them?
They're the same thing?
No, they are not the same thing, because one of them is a to power x, the other one is logarithm of x to power x. They are inverse of one another. Okay? How can I convince myself that these are inverse of one another?
Their inputs and outputs are swapped.
So how do you know? For example, let me calculate f of g of x to see if f undoes what g does. Okay? So let us calculate this one. How should I calculate this? It becomes f after g. G is this function. Yes? But f is acting on this number. Can you tell me what should I write in front? F acting on any input is a to power that input. But my input is now this one. Yes? So I have to raise it as a to power logarithm of x to the base a. Is that right? But can you tell me what is the answer to this? Is x itself. Can you see why? Can you see why? What? This is a very important formula. I have written all the formulas that you need to have in the notes. But why this is correct?
Because it's f of f inverse of x.
No, we don't know yet if they are inverse of one another. I want to convince you that yes, they are inverse of one another. The way that I want to convince you is to do it like this. I want to combine them, compose them, and show that f undoes what g does. It means that if f acts after g, as if it is nothing, nothing is done. I will go back to x. Why is that true?
Log base a of x is a number that says to which power we need to raise a to get x. And we're raising a to
that number. Exactly. Do you see that's a little bit convoluted? So if I ask you what is the, if you don't believe, let me do it in this way. What if, let me call this number n. Yes? What is the meaning of this number is n? It means a to power m is equal to x. Do you agree? That's the meaning. But let me take m. What can I do instead of? Well, I can replace m with one. With what? With this. This is your formula. Yes? Is that right? Mm-hmm. Do it the other way around. Gf. So it means that this is x. It's an extremely important formula. It's not a formula, it's just the definition of the logarithm. You see, logarithm of x to power a means the number so that if a is raised to that number gives you x. Now what you are doing? You are raising a to that number. So it should give you x by definition of the logarithm. Yes? Yes or no?
Yes.
Okay. So, but let us do the other way around. G after f. So let us see what happens. G waits for f. F acts, gives you a to power x. Yes? And now G acts on a to power x. So what should I write? A to the x is the input. So you have to replace your input with a to power x. So it becomes logarithm of a to power x to the base a. So what is the answer to this one? It means give me a number so that when a is raised to that number, it gives you a to power x. So what is that number? It's x. So you see, f undoes what g does, g undoes what f does. Yes? So they are inverse to one another. And if they are inverse to one another, the graphs should also be clear to you. For example, in this case, we learned that the graph of this function is of this type. Yes, y equals to a to power x if a is greater than 1. Can you draw the graph of this one for me? Or imagine it? Because we confirmed that they are inverse to one another, the graph of the second one should be the inverse, should be the mirror image of that with respect to the y equals to x. So let me draw that one. Yes, and if I draw the mirror image, it will be like this. Okay, what was this point?
1.
1. What will be this point?
1.
1 again. Yes, so this is y equals to logarithm of x to power a. And then let us investigate the limits. So the limit of logarithm of x to the base a, when I make x close and close to 0, if I am here, this is this much. If I am closer, it becomes this much. If I get closer, it becomes this much. If I get closer, it becomes this much. Okay? So it means that when I approach to 0 from the right-hand side, what do you guess for the limit? It becomes negative, negative, bigger and bigger and negative, so it becomes negative infinity. Yes? And then what is the limit of logarithm of x to the base a when x goes to positive infinity, or infinity, just simply infinity? So it means that if I am here, the height is this much, so I am going to the right and right. Of course, the increase is very slow, but if you go farther and farther, this becomes higher and higher. And then finally, very slowly, it becomes infinity. So the growth rate is very, very small compared to the exponential functions, which rapidly goes up. But it will not saturate. It will not get saturated at some point. Okay, so this is for the case that a is equal to 1. You should also be careful about what happens if a is between 0 and 1. Because we had two types of exponential functions. So naturally we will also have two types of logarithmic functions. Yes, one of them increasing, the other one decreasing. Any questions so far? Yeah, these are very simple things, but the calculation part might be a little bit... So have you seen these formulas before? So for example, I hope everyone agrees, logarithm of 1 to any base is 0. Why? Because any number by these conditions to power 0 is 1. So remember, logarithm of 1 is 0. That's one of the things you have to remember. But logarithm of any number to its own base, do you agree it should be 1?
Yeah.
Because a to power 1 is 1. And this one was the exactly very important formula we discussed about. And these 4, 5, 6 are also extremely important formulas. So logarithm of a product is the sum of logarithms. Okay, have you seen this before? So it means that for example, if I have logarithm of x times y to the base a, if x is positive, y is positive, a is positive and not equal to 1, you can write it as logarithm of the first one to the same base, logarithm of the second one to the same base, but not product, sum. And it is extremely important to remember the formula in both ways. Sometimes for some problems it is useful. This is given, you are supposed to go this direction. Sometimes you should be able to collect this back and go backward. So you have to be flexible in going back and forth. But for example, why this is true? So let me write it like this. So let me call logarithm of x y to power to the base a be m. For example, if you want to see why this is true, logarithm of x, I will call it. So let me write it like this. I will say that m is equal to this. This is the name I myself give to this. And I will give the name of, for example, n to this one. And I give the name of, I don't know, p to this one. Yes? If you want to see why this is true. Okay, can you tell me what is the translation of this? Logarithm of this number to the base a is m. This means what? This means a to power m is xy. This, what does this mean? A to power n is x. What does this mean? A to power p is y. Yes? But now I multiply them. So a to power n multiplied by a to power p becomes x times y. But there is another formula for this. I can write it as a to the power of n plus p equals to x times y. Yes? But now look, this one is xy, this one is also xy. So this means from these two, what can I conclude? That whatever a to power m is, whatever a to power n plus p is, they are equal. Because both of them are equal to the same number. But what can I conclude here? Exponential function is 1 to 1. So I know a to of some power is equal to a to another power. What can I conclude? M is equal to n plus p. But what was m? M was this log, n is this log, p is this log. So I was able to show that m is equal to n plus p. So any formula in logarithm you want to prove, you can prove it using the formula, a corresponding formula in exponential functions. So also this formula is very important. So for the quotient, if I have a fraction, the logarithm of a fraction is the logarithm of the numerator minus the logarithm of the denominator. So that's very good to know. And this is also very important. If you have a power up there, yes, this power can go to the back of the logarithm. So have you seen this before? Okay. And this one might be you haven't seen it before in the high school. This is the change of base formula. Okay, so what does it mean? It means that if you have where is the cleaner? Can you see? Well, it's here. So if I have logarithm, I don't remember what the letters I have used there. So logarithm of x to the base a. If you want, you can go to another base. So if this is a base a, if you don't like working in base a, you can work in any other plausible base. What do I mean by plausible base? A base should be positive and not equal to 1. So for example, let me say that b is positive and b is not equal to 1, and I prefer to work in base b rather than working in base a. This is possible. So then you can write logarithm of x to the base b, provided that you write logarithm of a to the base b. So it means that you can go to this base. I really want you to start thinking about why this formula is correct. But that has a very nice consequence, okay? So for example, let me work in the base x itself. So for example, let me write like this. Logarithm of a, b. This is a very nice formula. Do you believe that I can write like this? Why? I have chosen to, this is base B, but I have chosen to work in which base? 10, which I haven't written. So that's a very nice formula, okay? So can I write like this? Do you agree with this one? Yeah, so if I write, I can write it like this. It means that I have chosen to work in base A. Yes, for example, logarithm of A to base B, I work in base A. According to the change of base formula. So instead of working with base B, I decide to work with base A, which is the same number up there. But now, logarithm of A to the base A is what? Is 1, so it becomes logarithm of B to the base A. So those formulas that you see here, I hope you can see them, and if you have questions, you can ask me later, okay? But this is important to know. But according to the module, you should be very good in calculating these kind of things without calculator. Okay, so let us do some of them together. So the first one and the second one are easy. Can you do the third one? So what is the logarithm of 1 over 27? So logarithm of 1 over 27 to the base 3. There is no one unique way to do it. Okay, first of all, you might be good in numbers and you can guess. So can you tell me what is the number so that 3 to power that number is 1 over 27? Yeah, because 1 over 27 is 1 over 3 to power 3, which is 3 to power minus 3. So it's not hard. So immediately, if you can calculate this, the answer is, of course, minus 3. If you cannot calculate it, you can say that this is a fraction. For example, the logarithm of the numerator minus the logarithm of the denominator. These are very important formulas. But logarithm of 1 is always 0, and logarithm of 27 base 3 is simple. 3 to which number is 27? It is 3, but there is a minus sign here, so again it becomes minus 3. So there are different ways you can calculate these things. Okay, so for example, one might be a hard one, might be the last one is hardest, but might be this one is also good. Can you see how we can solve number 7? We have 3 to the power of a fraction. The numerator of the fraction is 4. And the denominator is a logarithm whose base is 7. Yes? Of course, you have to look at the formulas if you don't have all of them in your mind now. So, I will write it here for you in a little bit clear way. So it is a 3, big 3, divided to a small fraction like this. 1 over logarithm of 9 to the base 7. Yes, I will wait for you a little bit. Can you help me to solve this?
And what it was 4 in the numerator?
Which one? 4 is in the middle, thank you. 4. Yes. Do you have any idea?
We can sort of split the fraction, so we can say 3 to the power of 4 times 3 to the power of 1 over the log.
Not 3 power. Yes, you are more or less right. You are. I hope you mean this.
Yes.
Because that one you said is not correct. Can you say it again? You told me what?
3 to the power of 4 to the power of 1 over...
To the power. But you told me multiplied.
Oh.
So this one you mean?
Yeah.
That is correct, yes. To the power of?
1 over log base 7 and... yeah.
It's not wrong. This equality is indeed valid. But you have to see if it is useful or not.
We can flip the log. So
Flip the log. I will follow you. Okay. So 3 to the power 4. Can I flip the log? Yes. The price I have to pay is to swap these two. So it becomes 7, 9. Okay then?
And then the base is...
The base is 81. 3 to the power 4 is 81.
Right, but I'm talking about the base of the log.
Yes, so you want to have it... okay, here.
Right.
Yeah, there is no one unique way, but that's correct. If you don't mind, let me write it as 9 to the power 2. Yes?
Okay.
Instead of this. For example, I'm not saying that this is the only way. And then what should I do? I don't know. I multiply it back again. So it means that I am not doing it in an efficient way. I'm just following what you started. And then this 2 is an obstacle. So for example, I can move it up there. I mean, this is one way. And the answer will be 49. Yes. So I am not saying that what we did on the board is the best way. You might be able to find another way. But hopefully you understand what I am doing is legal. Yes? So instead of, I hope that everyone agrees that this is correct, because a to power x to power y, I can write a and multiply the exponents. So it means that I can write 3 and multiply these two. When I multiply these two, I get this back. So this is valid. Yes? And then we used 1 over this. I flipped them. That's another rule that I explained here. So that's also valid. But then I realized, okay, so this is 9. This is not 9. I want to use this formula somehow. But for that, I need these numbers to be the same. So that was my strategy. So I will try to see how can I do that. So instead of 3 to power 4, which is 81, I wrote 9 to power 2. But the motivation behind that, I want to get closer to making them the same. Okay? And then, of course, this 2 will be multiplied here. But if this 2 was not there, I was done. But unfortunately, 2 is there. I have to get rid of it somehow. Then I realized that this number 2 can be flipped on top here. And it becomes 49. And everything is now ready. So this becomes 49. Again, why I'm saying this is not the only way. You might sit down and find another way. That's also correct. But the final answer is 49. Is that right? Okay. For example, because we don't have that much time, let me at least solve one problem for you, and then this is the first time that there are many things left. Yes, many things left. Yeah, I will try to find a way from the next lesson to compensate for what is left. Okay, how do you think we will solve example 8? So you think I will write it on the board and then we start. This is the question that I have chosen from the course book. So we want to simplify this a little bit. Okay, since there is no time, so let us do it together. So do you have any idea at least? Yes?
Yeah, first you have an addition of logarithms, so you multiply them.
You multiply them. Can you do it all of it together?
Yes.
You can do it step by step. There is a plus sign here. We can combine them. But there is a minus sign here, so it means that this 2 will go up there. And then because of this minus sign, it will go to the fraction. So if you want to do it all one together, so I hope that you can understand what I am doing is correct. I mean, in the exam, might be it is better to write it step by step. So, but I hope that everyone agrees with this, what I've written. Is that right? So this plus multiplies them. This 2 goes up there, but because of this minus sign, it goes to the denominator. If you are not comfortable with this, practice on this at home, do it step by step. But can I continue a little bit more? This is the conjugate rule, so it becomes 1 minus cosine x squared divided by sine x squared. But what is 1 minus cosine x squared? Sine x squared x. So this becomes logarithm of pi sine x squared divided by sine x squared, pretending that everything is fine and defined. So this fraction becomes 1, but logarithm of 1 to any base is 0. So this is the simplified version. Yes, there is no way. We have to find a way to fix it later. Okay, because there are many things left. Any questions? Thank you.